This sample problem deals with a two-dimensional inelastic collision. We have two lumps of clay, a 0.3 kilogram lump of clay going west horizontally, no vertical motion, through the air at 6 meters per second, and a 0.8 kilogram lump of clay also traveling horizontally, no vertical motion, but at an angle of 40 degrees to the north of west at 9 meters per second. They'll collide and stick together, so it's an inelastic collision. We want to know the velocity of the package, the 1.1 kilogram combined lumps of clay, in the horizontal direction after the collision. We're not going to do anything in the vertical direction. There, of course, in air near the Earth, there is a force of gravity acting vertically. We're not dealing with that at all. This is a problem just in the horizontal direction. And once we get the velocity, we want to know, is kinetic energy conserved? So a problem-solving method would be to read through the problem a couple of times. I'll let you do that. And then make a sketch. So I'm showing the 0.3 kilogram object at 6 meters per second, 0.8 kilograms at 9 meters per second, but at an angle here, 40 degrees north of the west line. So let's go through another slide here. We have a summary of the data, the masses of the clay objects and their velocities, and we need to keep in mind it's an inelastic collision. We want to know, is momentum conserved in the horizontal direction? And the answer is yes, and we're going to ignore air resistance. Any force of air resistance is a small number in practical terms. And we're not dealing with any vertical motion, so we don't have to deal with the force of gravity. So there's no external force on our system of the two clay objects. Therefore, momentum is conserved. It's conserved in the east-west direction and in the north-south direction. And we're going to find those components, so we'll do two calculations. So let's see how that proceeds. In the east-west direction, I'm choosing west to be the positive direction, and you can see on the diagram north is also my choice for the positive direction. In the east-west direction, 0.3 kilograms times 6 meters per second is the momentum of the first lump of clay. Momentum is mass times velocity. For the second lump of clay, it's a little more complicated. The 9 meters per second is not an east-west number. It's not a north-south number. We have to find the component of this 9 meters per second in the west direction. We do have a right triangle. I didn't draw it in, but it's there. A 40-degree angle down at this corner. And the cosine of 40 degrees times the hypotenuse of 9 meters per second gives us the westward component of the velocity for the 8 kilogram object. So that's what I use to calculate its momentum. You might want to pause the video and pull out your calculator. For the sum of the momentum of the two objects, I got 7.316 kilograms meters per second. I tend to keep 4 digits in my intermediate answers and only round to 3 digits at the final answer. We'll get to that in the next slide, or the 2 slides. In the east-west direction, after the collision, momentum can't be a single number. We don't know the velocity yet in the east-west direction for our 1.1 kilogram object, so it's an expression. But we equate the two. The east-west momentum, 7.316 kilograms meters per second before the collision, equals the momentum in the east-west direction after the collision, this expression, mass times the unknown velocity. Well, divide by 1.1, I came up with 6.651 meters per second. Similar process in the north-south direction, but it's easier. In the 3.3 kilogram clay calculation, its north-south velocity is 0. It has purely west velocity. So mass times 0 meters per second for the north-south velocity. And then in a similar manner, the 8.8 kilogram lump of clay, we have to find the northward component of its velocity. If our angle is down here, 40 degrees, the opposite side to that angle we use the sine function to calculate that component of the 9 meters per second. And I came up with 4.628 kilograms meters per second. We also don't know the velocity in the north-south direction for our lump of clay after the collision. That's what we're trying to find. So it's an expression, but we equate the number we have before the collision for momentum in the north-south direction equals the momentum after the collision. And in a similar way, divide by 1.1, I got 4.207 meters per second for the velocity northward. Now let's reconstruct and get the velocity vector, the magnitude of the velocity, and the angle of the velocity of the 1.1 kilogram object. And we'll think about, are these numbers reasonable? So just copying the numbers from the previous slides, westward component of the velocity 6.651, the northward component 4.207 meters per second. We use Pythagorean theorem to find the magnitude of the velocity. V squared is equal to the sum of the squares of the other two sides. And to find V, we have to take a square root of this whole equation, one side at a time. So you should again pause and do this on your calculator. I came up with 7.87 meters per second. That's the magnitude of the velocity. Is this number reasonable? In a sense it is, because the hypotenuse of a right triangle is always larger than either side, than any side. So 7.87 is bigger than both of these two speeds, and it's reasonable in that sense. To find the angle, it's a little bit more complicated. The tangent of the angle is equal to the opposite side divided by the adjacent side to this angle theta. So tangent theta is 4.207 divided by 6.651. We want theta, we don't want tangent theta. To remove theta from control of the tangent function, I apply inverse tangent to both sides. It's important to do it to both sides. So inverse tangent of tangent theta produces theta. The calculation of the 4.207 divided by 6.651 is 0.6325. And on your calculator, if you put your calculator in degree mode and take inverse tangent of this number, you should come up with 32.3 degrees. Is that reasonable? Well, if you remember, our 0.8 kilogram clay mass was coming in at 40 degrees north of west, but it made a collision with an object that's hitting it this way. So it is reasonable that the angle is smaller than 40 degrees, so 32.3 degrees. What about the kinetic energy? Is that conserved? Do we have the same amount of kinetic energy after the collision as was present before the collision? Well, 1/2 mv squared, 1/2 mass times velocity. So I do that calculation separately before the collision. There were two separate objects, each with a mass and each with a velocity, and I came up with 37.8 joules. After the collision, there's one object, 1.1 kilograms. In the previous slide, we found 7.87 for its speed, its magnitude of its velocity, and I come up with 34.1 joules. And not surprising, the kinetic energy after the collision is smaller than the kinetic energy before the collision. Kinetic energy is not conserved for inelastic collisions, and I'll let you read about why the energy is not conserved. Where does that energy go to? Ask your instructor if you have questions on that, but that's not the purpose of this video. Well, I do have many other videos for physics and astronomy. You can find a list, an annotated list of my YouTube videos at my simple website, gpclements.com. The annotations are grouped by topic, by their category of physics, concept, Newton's laws, angular momentum, etc., centripetal force, gravity. In the annotated list, there's a link to the YouTube video, a direct link. You don't have to search on YouTube for my video. You can click on that link. The annotation shows how long the video is, how many minutes, and describes what's being calculated. All the content that I create is free. There's no charge. You're not allowed to sell it to somebody else. At this website, you do not have to give me your name or your email address, anything. And my website does not put cookies onto your computer. So keep working sample problems and ask your instructor when you have questions.